Hi, let's have a look now at paper 3 of the PhD thesis. It's called Optimizing Green Lidar Point Density for Accurate River Hydraulic Simulation and Environmental Impact Assessment. It contributes to Objective 2 by quantifying the deviation that raise from using lower resolution terrain data and investigates the optimal point density required for accurate analysis. So, what we did in these two study sites where we have very good LIDAR data sets was, okay, let's create different data sets with less density. So for both of the terrain, we have PD16, terrain 1, PD16, that has 16 points per square meters. The second dataset, PD4, has 4 points per square meter. The third one point per square meter. P025 has 0.25 point per square meter, meaning that we have 1 point every 2 meters. 0.04, we have 1 point every 5 meters, 0.01, a point every 10 meters. And the first one, PD16, 41, will be something that we will more typically get with LIDAR datasets, while the last one will be more typically taken by ADCP or a GPS. So for each of the terrain, we have the densities. In the first one, PD16, 16 points per square meter. You can see here 1 square of a meter with 16 points. We create a triangulated irregular network, thin surface, triangulated irregular network, and then we interpolate a raster with 0.25 meter resolution. And this is so for each of the data sets. And this is important because at the end of all the data sets have the same raster resolution, 25. And we have interpolated between the previous, since the main point cloud to the final raster as much as we could. Yeah, you can see an example for PD16 and PD0.01, and you can see that we only change the bathymetry, the riverbed, while the floodplains remain the same. You can see here very dense cloud, you can see here the cursor. Remember, because I will use them again, PD16 is the finest dataset, 16 points per square meter. PD0.01 is 1 point per square meter. And I want to also point out, like, even if PD 0.01 is like we have 1 point every 10 meter, this is also very optimistic, meaning that if we have a very large river like this one, Nidelva here that we have in these pictures, there are some areas where it might be very difficult to get a point. Maybe because it is too deep, maybe because velocities are too high and we cannot get there easily. So actually having a point every 10 meters is a very good data set. And if I was meant to do this study again, what we will do, we will increase the study to even coarser data set. Okay, what if we will have a point every 100 meter or every 20 meter? But now we have this research, so let's keep on talking about it. Remember, we only change the bathymetry, not the floodplains. Yeah, because the floodplains are actually already measured with good LIDAR in Norway. This is not the case for all the countries in the world, but this study was focused in Norway, so we thought, okay, we assume that the topography, the part that has no water, is already well measured. What if we also have the bathymetry? And this is an example of a result. We can see the points are the calibration points, points that are taken with a GPS. And this point measure X, Y, and Z. It means that they measure the water surface elevation, but they also measure the exact location of the river edge. We go with our GPS to the river edge and we measure the edge. These results are shown for PD16 and PD 0.01. Remember, 16 points per square meter and 1 point every 10 meters. And this is also after calibration. We have created each of the model and calibrate for different money numbers to make the best fit that we could to our calibration points. And what we see is like it's well matched for PD16, but a less precise fit for PD001. And we even see a side channel forms incorrectly. It means that we have seen here a side channel that it actually doesn't exist. And we find the same in the Lardal case. We see the points for calibration points and the inundation boundary for PD16 and 01. And what we see, it's actually the opposite. A side channel is not accurate model. And I mean, this is something we could assume that what's going to happen. PD16 is a lot more accurate than PD 0.01. But the magic here, or the good thing of this research, is that we actually quantified. So we did, for example, these graphs for inundated area difference in both Estorane and Lardal. I'll put myself up here. So what we see here are the flood scenarios for a return period of 10, 50, and 200. So we can see the inundated area difference is not as big for these three. These are the smaller errors. While for low flow scenarios, average flow and minimum flow, we find the largest error. You can see are the purple and the blue line. That means that the error goes up to 24% in the case of Estorane for PD 0.01 and up to 15% for PD 0.01. What we could see, or we could use the famous word significant impact, but yeah, that depends of what you consider significant, but we can say, okay, we might have a 24% error if we use bathymetry or a bathymetry that has 1 point every 10 meters for Estorane low flows. We also do this study for depth and velocity. So we see here depth, velocity for Estorane and depth and velocity for Lardal. For the same, this is for the flood scenarios. And what we see is that the biggest dispersion, we got it for the case of PD 0.04 and 0.01. So actually, for the rest of the PD 16, 4, 1, and 0.25, errors are even sometimes less than 5%. So we don't see great changes between 16 and 0.25. While for the low flow scenarios, we see significant changes for PD 0.25, 0.4, and 0.1. So this has been applied in two study cases, Lardal and Nestorane, that have a given average flow and a certain river size. I do think that this research should aim, or following research or future research should aim to see, okay, how is it for other river channels that are larger flows or smaller flows, because this might change. But if someone asks me, okay, we have to survey a river and it's similar characteristics to Estorane and Lardal, and we want to do this kind of simulations for flood and low flow scenarios, I would say, okay, for the floods, I think with a density of 0.25 or 1 might be enough if we get more better, but with 0.25 or PD1 might be enough. While if we're going to make the low flow scenarios, we might aim for at least having 1 point per square meter. So these give us a base to study further this density that we should aim for in future studies. And yeah, I hope it helps, and thank you for coming here. We will continue in the next paper of mitigation of environmental effects of frequent flow ramping. Thank you.